and thanks, Raphael, for that last talk. I think not only an example of genealogy in physics, but also of Darwinian evolution, where two theorists make one modern hard condensed matter quantum optics experimentalist. So I first met Emmanuel at what was ITP, Institute for Theoretical Physics, in 1994 in Santa Barbara. And there were two programs going on at that time. There was one on vortex phases, and there was one on membranes. And I was in neither of those programs. I was on sabbatical, and so I could wander around the building. And I wandered around, and I saw Emmanuel, whose work I knew from membranes. And he was sitting there calculating and very welcoming. And I just went in and we started talking about folding. And I learned about the beautiful work of Emmanuel and Philippe on the planar folding case. And I studied that paper. And I still have little paper models of hexagons and the 11 vertices corresponding to the folding configurations. And I still have transparencies that we used in those days. I think that was the three coloring that arises from the planar folding problem. And we just talked and decided the two-dimensional problem leads to a first-order phase transition. So if you're really interested in describing continuum membranes, that is a pretty extreme discretization, but a very beautiful one, and it leads to a first-order folding transition. As an attempt to really understand whether the continuum system has a continuous crumpling-like phase transition corresponding to folding, we decided to, with Philippe, to extend the folding into 3 dimensions, but still with a discretization. And that led to this study of octahedral folding, which is a discretization of the 3D R3 as a face-centered cubic lattice. And you have octahedral folding, and this 3D is tessellated by an octahedron and its dual tetrahedron. So the tetrahedron featured prominently in that work. We continued that work for a few years. In 1997, I came here for 3 weeks on a sabbatical, and I remember Henri had to send me out of the country so that I could come back on the visa, since it only lasted 3 weeks. He was the chef at that time, so that was fun. And so in 3 weeks, Emmanuel and I managed to write another paper, which was on the tubular phase of membranes and the effect of self-avoidance and calculating the critical exponents associated with that system, bringing back the self-avoidance work that Bertrand talked about earlier. Then there was a gap in our collaborations, but 2007, I came back here on sabbatical, so I was here for 6 months, and Saclay here was a very wonderful, welcoming place to work in that time. And what I remember most distinctly was coming here beginning of January, and we had not been working together, Emmanuel and I, for a few years. So the first month just consisted each day of sitting down and mentioning some problem. Here's this problem I'm interested in. Here's a problem Emmanuel is interested in. And okay, we discussed that. That's fun for the day. Then another day. Then another day. And one day after a month, I just mentioned this problem of dimers on 2D square lattice. But if you know the game of 15, where you have 15 numbers with one missing square, randomly organized, and you have to move it around to get them into the order 1 to 15 in sequence. There's a generalization of that where you don't have square tiles, but you have dimers, so they're rectangles, 2 by 1. And there's one, that's problem solved when it's fully packed, everything is covered, but with one vacancy that models a kind of motile particle in the system, it's a more challenging problem. So immediately I saw Emmanuel's eyes light up. And you could see that he was already thinking, this one is interesting. Finally, he's mentioned something interesting. And that's when we started working on that problem. I'm not going to talk about it in detail, but here's a couple of the images of spanning webs that came out of this paper. We computed the probability of this vacancy here, or monomer, being actually completely jammed. So there's only one, basically, site available to it. And there are lots of nice irrational numbers that have come up today, and they'll come up again today. And the probability that came out of that was actually sort of numerically extrapolated by computing this probability and looking at 1 over the square root of it to many, many decimal places, and then using the Plouffe inverter, which was Emmanuel's idea to actually guess or deduce what the solution analytically was. It shows that the system is jammed in the infinite system size, and also that the system is what we called weakly localized. So the probability that this vacancy can actually escape, percolate, if you want, in the infinite volume limit is 0, falls like 1 over L to the 1/4. About 7 months later, this value was actually analytically computed by a group, 2 Russians and a Ruel in Belgium. So that was fun. Again, my most distinct memory of this work was writing the paper, sitting in Emmanuel's office, which is just across from his current office there, and we discussed word by word, I remember, word by word, what we should write, made the figures, xfig, which Emmanuel is an expert, as most of us here know, and we would write, and then look out the window, and I thought, yes, this is why I went into physics. Now, what I want to do today is actually just to give Emmanuel some problems to work on, because he doesn't have enough right now. So. And the first one I want to start with is a problem related to symmetry. It's kind of drilled into us in our education, at least for me, to exploit all these symmetries of a problem in solving it. But that can lead you very far astray, as we know. Here's a problem which is very, very simple, 2-dimensional problem, planar. You have just a square in the purple here, and you want to build a mirror that will block light that goes from any side to any other side. And you just don't want to build that mirror. You want to know what is the graph or map of that mirror that minimizes the length. Okay. So of course you could go around 4 sides. That would give you length 4. Or you could do 2 diagonals, which gives you 2 times square root of 2. And then anyone who's made, knows minimal models, made soap films, anything like that, would think of inserting an interior vertex into this graph. And that would give you this kind of diagram here, which has length 1 plus square root of 3, around 2.7. Well, that's not the optimal solution. And the optimal solution is very, very counterintuitive because it's not connected. It has 2 connected components. and it has one interior vertex or Torricelli point or Steiner point freely terminating here. And the other is a threefold vertex. And once you think about this kind of structure, you can compute that angle there by minimizing length, and it's 15 degrees. And this length has root 2 plus root 3 halves. So it's significantly less than this one. And if you look at the original problem, it has 8 symmetries, 4 rotation symmetries, 4 reflection symmetries. This solution breaks 7 of those 8 symmetries. It only has 1 left reflection along this diagonal, and it has the emergent topology from one connected component to 2. So this thing called the opaque square problem, or you can also think of building a trench of minimal length that will uncover, a telephone line, a cable, something that goes from one side to the other side. Yes.
Maybe I missed
Yeah.
What is the problem? What is the constraint you want to
Minimize the length. The constraint is that you have to block. You have a mirror. You have to block light that goes from any edge to any other edge. Going across like that has to be blocked by the mirror.
And the way is the mirror is a red line, right?
Yes.
And there is no way to pass.
No. No. Where? Go from here to here is blocked by that. Go from here to here is blocked by that. Go from here to here is blocked by that.
You cannot reflect on the red line.
No? How?
No, the red line is not a mirror.
The red line is.
It is a mirror.
Yeah. Try to go from here to here. It's blocked by there. Here to here. Blocked by there. Goes to the midpoint here. No, no, if it's not clear.
I had the impression that you could go from the bottom and burn one of the red mirrors on the left. And
No, you hit this one.
but you mean it has to be vertical direction?
No, any line from here, this edge to any other edge, this edge to any other edge has to hit the mirror.
Maybe one wants to think about them as walls rather than mirrors.
They're lines. The mirror is a line. It's in the plane. It's a 1D mirror.
No, okay. You don't say that the ray of light starting from the boundary can exist. There could be a light coming from the bottom.
No, it's confined in the square. Is it clear? What I?
Prevent you from bouncing against the left.
Oh no, just one path. One edge to other edge. Bouncing back.
If you go left,
No, to another edge.
no, but if you left, bounce against the left mirror, and then go right.
It's blocked by here. No, you own one path, one single path.
This is Jeremy. Can I do this? Boom, boom.
Oh, one path. It's got blocked, just be blocked once. Not multiple reflections. Not multiple reflections. One path. Single path. Yeah. No reflections. There it's blocked by that. That solves it. Yeah. Okay, good. It's a classical 1D mirror. It's a fully mirror. You listen to too many that one experimental talk has converted you into. Well, these are here sorry. E.g. here is hold it. Why isn't I'm holding it now? Okay, the problems for Emmanuel there in the double green line is to generalize this from the foregone, the square, to an n-gon. Okay? So first of all to an n-gon, pentagon, hexagon, and so on. You can find a similar kind of construction and can compute the length of that mirror, that 1D fully absorbing mirror that blocks light. And then you can compute that length and then take the limit, n goes to infinity. In which case, geometrically, you would expect to get the circle of length 2 pi. And this system gives you a solution. That construction gives you a solution whose length is pi plus 2. It's like 80% less than 2 pi. So that's one exercise for Emmanuel. Philippe talked about the folding problem, and the beauty of the planar folding problem solved by Emmanuel and Di Francesco is that it really reveals the difference if you're thinking about the continuum physics of the elastic membrane that Bertrand described. It's already remarkable that that system has a low temperature ordered phase. If you think of it as a two-dimensional system and you think of the normal vectors to the surface as like ferromagnetic spins, thermal fluctuations should disorder it in 2 dimensions. However, it's not a simple two-dimensional system because it's really a manifold. It's really an embedding of that surface in R3, which gives it a character somewhere, between 2 and 3 dimensions. It's a mapping, an embedding. But in this solution, you can compute, in the planar solution, you can compute the entropy of folding and the corresponding number of degrees of freedom per site, which again involves square roots of 3 and gamma function of 1/3 to the 3/2 power. Some beautiful irrational numbers coming in there. And that's of order 1.2 compared to thinking of these normals as spins, which give you an Ising system with Z2 symmetry with 2 degrees of freedom per site. So the fact that you have basically no local degrees of freedom, and you can see that because folding is non-local. The folding lines extend all the way across the lattice. So this already shows you that the system is very different from a two-dimensional ferromagnet. Furthermore, having zero local, no local degrees of freedom means that the global folding of the system means that you would think that there are actually no local degrees of freedom because the folding itself is global. And what Emmanuel and Philippe showed is that you can understand the entropy. What is the entropy of folding? There's actually degrees of freedom associated with unfolding the fully crumpled system down to one triangle. So that's a very, very, I think, beautiful insight that helps you to understand why the elastic membrane has this critical ordered phase, long-range order in the normals below some critical temperature, and how it differs from a ferromagnet. As was mentioned in the octahedral folding problem, this should, see, you get a 96 vertex model. So the tetrahedron features fairly prominently in this work. So now I want to show another way of getting a tetrahedron, one of the world's most complicated ways of getting a tetrahedron. And that is if you take a liquid crystal, a two-dimensional liquid crystal, so you have nematic order. A nematic in 2D is a line field rather than a vector field. So the space you're working with is the real projective plane, RP1. There's another reason why the system is different from a ferromagnet, because projective space has a completely different structure from the vector case, which would correspond to, would not have the inversion symmetry of the projective plane. So if you take a system whose Hamiltonian is a two-dimensional liquid crystal plus the bending energy term, that mean curvature squared that Bertrand talked about, where the order field is on RP1, that's the nematic, and the topology is some closed, start with the topology of the two-sphere. If you have a hole in the system, that has a line tension, so the system will like to spontaneously close that hole because the rest of the Hamiltonian is scale invariant or conformally invariant, as Bertrand mentioned. So in general, we can work on the two-sphere. And the interesting thing about this problem is you have to, in the extremization problem, you have to determine the manifold as well as the order of the state, of the ground state. So what you can show, there are two coupling constants in this problem. There's a modulus of the liquid crystal I call big K. This doesn't. Oh yeah, first the two. And then, yeah, but I'll use this. So there are two parameters in this problem, which are the bulk modulus of the liquid crystal K, the Frank modulus of the liquid crystal big K, and the bending rigidity little kappa. By the way, this term was not first discovered by Helfrich, but by Sophie Germain in 1811, for which she won a prize for this. So this should be the Sophie Germain Hamiltonian, really, this term here. So let's look at the limit where the bulk modulus dominates, the Frank modulus of the liquid crystal dominates compared to the bending rigidity, so the low bending rigidity limit of this system. That means you first want to extremize the liquid crystal piece of the Hamiltonian. So that means that the system wants to be uniform nematic order, but you also want it to be flat, so the covariant derivative doesn't contribute to the gradient. So you want the system to be flat and uniform nematic order, or uniform ridges, stripes. That would be another limit of the system. But the integrated Gaussian curvature is non-trivial, 4 pi, because of you're on the topology, you're on the two-sphere. So how do you solve that problem? You can actually solve it by having the system as flat as possible, which means you want planar flat facets and just all of the Gaussian curvature concentrated at discrete points. And the minimum number of discrete points to define a non-degenerate surface would be 4. So that suggests the tetrahedron as the ground state solution of this problem. That's indeed the case. So here you've given not only the order from the original problem, but the shape that the system should live on. So this means that this limit, and you make, say, from a vesicle, a liquid crystalline vesicle with the topology of the two-sphere, in this limit, it should spontaneously facet to this very sharp structure from a very smooth-looking initial problem. So that's the facets of order I was talking about. And here is what happens is that not only is the Gaussian curvature concentrated at discrete points, but the nematic order also has to have singularities or zeros of the field, as again required by the Poincare-Hopf theorem version for a nematic, for an RP1 field. And the defects associated with the nematic order are also concentrated at the vertices of the tetrahedron. And you'll see here, if you go around a vertex, you turn 180 degrees and come back to the same line field going around a vertex. So this is the basic topological defect of a nematic field of the RP1 field. There's a 1/2 singularity, plus 1/2 singularity at each vertex. So you have singularities or zeros at the vertex for both the Gaussian curvature and the nematic order. So this was some work that we published in PNAS in 2012. And you can generalize this nomadic order, which is like a two-fold order. Vector order would be one-fold order. You can generalize this to two-fold, three-fold order, and so on. This will give you a polyhedral surface order 2p. So p equals 3 gives you 6 vertices, which is an octahedron. P equals 4 would give you 8 vertices, which is a cube. And on each face of the cube, you'd have 4-fold order. P equals 6 gives you an icosahedron. So my challenge for Emmanuel is to think about the case P equals 5 and to see whether perhaps there's some kind of quasi-crystalline version of this construction, which would probably require two components like the two tilings of Penrose tiling. So that's the second problem. The third problem, recently we published a paper with Ivan Smalyuk's group at Boulder and his student Jason Wu and a student of mine, in which experimentally you can actually realize what's called a biaxial nematic. Biaxial nematic, which was worked on here by Toulouse and Polonaro and several others 50 years ago, is a beautiful system where you have two orthogonal director fields. Now, not just one. Okay? So therefore, you can have defects circulating one director or the other director or both. And you can have a +1 like defect, which is unstable for the uniaxial nematic to escape in the third dimension, which is obstructed here by the non-trivial topology when you have this biaxial order. So the fundamental group that controls the classes of defects in this case is pi1 of SO3 mod this biaxial symmetry, the symmetry of a brick like this with two different axes that are orthogonal. The fundamental group in this case is the group of quaternions. So you have three like complex numbers I, j, and k, that's squared to -1. You have this third radial component, it's called here -1, and then you have the identity. So 5 basic classes here. These are 3D, now we're in bulk 3D. This gives you 3D line disclinations as the defects, and you have entanglement, topological entanglement, again as envisaged by Polonaro and Toulouse in the 1970s. And the entanglement is the following. So now we have colored objects. We have these 3 colors I, j, and k, and then the -1 defect. If you take 2 distinct line defects, I and j, say, there's a topological obstruction to disentangling them, to crossing them, because you have to produce, if you work this out, the element, the obstruction in between is a -1 defect. So if you pull this, if you try to do this, you create junctions. And of course, there are basic junctions in the algebra. I, j makes k. So you have 3 colored trivalent vertices here again. So 3 coloring, okay, Emmanuel. You can realize this experimentally. Biaxial nematics are hard to make, but you can realize this experimentally with a chiral nematic. So chiral nematic is nematic for which you also have a chiral twist in the system. So the twist will give you the second axis without having to have a building block that's biaxial. So you have a director, and you have the twist, and then you have the cross product, which gives you the 3 axes. And the chiral nematic is an experimentally realizable system, so you can actually make these defects, and you can see the entanglement, but in particular, you can see the junctions. And with junctions, you can make networks. So this means if you want to understand the networks you can make and the topological kinds of knots or knotoids or all of the structures you can make in this system, you need to do braid theory with these 5 different colors or 4 non-trivial colors and this quaternionic algebra. So these are completely unclassified. So there's another problem for Emmanuel in the coming years. Last one is a problem related to another kind of pneumatic-like system, which is a ridge system. So if you look at your fingerprints are lines or ridges. So you have a structure that's like this. So it's also described by the same kind of Hamiltonian we were talking about. And it's known phenomenologically that these ridges go parallel like this along a finger. So they're sort of normal to the boundary of a finger everywhere. But at the tip here, they don't turn normal. They just stay horizontal at each tip. So the ridge system has the same defects as a two-dimensional liquid crystal. So you have the fundamental group is the integers, and the basic defect is this defect I showed before, where you rotate by 180 degrees going around a defect. That's a strength. 1/2 defect, looks like a comet. The rotation in the opposite sense is this -1/2 defect here with this threefold symmetry. This has a threefold symmetry, this has twofold. It's interesting. Now supposing you want to, first of all, if you look at your fingerprints, you'll see both these kinds of defects. This is called a loop, this is called a triradius. So you can look and count them. So supposing you want to know something about the net number of defects on the system, on your hand. So you can start with a loop down here with this nothing, contour. As you extend your contour, every time you cross a plus defect, you'll get +1 contribution, a minus defect, -1. And you're counting topological indices, so it's invariant under the contour, so you can take this external contour here. Now this external contour here, the only defects that occur are here at the spaces between, at the valleys, the spaces between fingers, where you see that the ridges have to rotate 180 degrees in the negative sense. So each spacing between fingers gives you a -1/2 contribution. So the net number then of defects, the number of +1/2 minus the number of -1/2 is just the number of gaps, which is the number of fingers -1. So we started with the world's most complicated way of making a tetrahedron, and this is probably the world's most complicated way of counting how many fingers you have. It's pretty interesting that there are more -1/2 than +1/2. So my problem here for Emmanuel is, first of all, I think you could probably think about the system using Morse theory, where you have indices associated with the mountain peaks here, and with the valleys here, and possible saddles. But also if you think about the topology here is essentially planar. So understanding why you get this net number of defects on this kind of topology, I think is maybe the proper topological setting for this problem is an interesting challenge. So I have been very much influenced by Emmanuel's work. The thesis that Bertrand mentioned sits on my desk, and I go and read it every now and then, and I give it to my students to read. Every time I see these kinds of coloring problems, especially the three coloring, shapes, graphs, and so on, I come across a problem, I send an email to Emmanuel, see if he knows the answer. And I look forward to him getting back to me with some of the solutions to these problems that I've mentioned today. And I will end with one problem that is another fun one, which actually, unfortunately, it was solved just in the last 2 months, probably many of you know about this problem. It's the moving sofa problem. You have just a corridor with one right angle turn, 2 dimensions. And you want to know what is the shape of the sofa of maximal area that can be translated and rotated. That's all you have, translations and rotations around this 90-degree turn. So this is again a problem where you have to determine a shape with some property from a very, very simple looking setup. And of course you can use a square of area 1. You can use a semicircle like this, semicircular disk of area pi over 2. And the actual solution, so you want this kind of structure in the solution. And the actual solution was found here just a few months ago. This is the basic shape, and here's the shape in more detail. It has 18 separate segments. It has this semicircular disc built into it, but it has all these nicely shaped pieces to it. And the area is 2.2195. So there may be some interesting generalizations of this problem. Okay, thank you.
Thank you for this very entertaining talk. Any questions?
Yes, on this shape, is it the one which was conjectured for 20 years?
Yes, McGurver, it was. And that drove, of course, a lot of the work. But it had to be, somewhat reformulated to prove that is the exact solution. And that required all these kind of refinements. But absolutely, it was the conjectured solution. Yeah. Yes?
In the case of the opaque square,
yeah.
you showed the geometry of the answer.
Yeah.
If you generalize to angles, do you have a conjecture of what the shape of the optimal answer is?
Yeah, it is known. You draw those kind of, you draw the analog of this across from one vertex to another, and you have a whole nested sequence of those. And then you can compute the length, and you compute the length just using trigonometry. Once you have the idea of sort of the disconnected piece, the freely terminating piece, then you can generalize that, and then you can take the limit of n goes to infinity by a geometric series. Yeah. So that part is actually known. So Emmanuel has to reproduce that without looking at the solution, but I bet it'll give you perhaps different ways of thinking about it. Yeah, I can show you it's a really nice construction, and the pi plus 2 limit, so far from 2 pi, it's really remarkable. Something about n goes to infinity limits. Yeah.
Okay, no more questions?
Yes, Jeremy.
Jeremy. Yeah.
Okay, it's not a question. It's an anecdote. It's an anecdote because I think we are also here to say things. You said something about the expertise of Emmanuel in XFIG.
In XFIG.
Yeah, XFIG. Yes. So okay, so I have to say I did it in my talk, but one of my memories when I started my thesis with Emmanuel and Philippe is that at the time we were not typing papers with LaTeX, but with a tech variant called ARMAC. Okay, maybe you used it too. It was in higher physics, maybe. So I knew ARMAC. Yes. Yeah, you remember. So I hated ARMAC. It
orders but the references orders nicely.
Yes, it's good. And I said, "Oh, I know LaTeX. Why do you use that?" And they said, "You are the student. You don't decide. You will use ARMAC." And then we let evolution go on, and maybe 10 years later, we were all using LaTeX. That's it. And XFIG. Okay, we also use XFIG, and actually, I love the XFIG. Emmanuel managed to convince me, and I love XFIG. But I think, I'm afraid to break it to you, that I think he's now using IPE and not XFIG anymore. But I think he found a good equivalent. Am I right, Emmanuel? But you proved it.
Yes. Bertrand benefited tremendously, I remember, also from Emmanuel's expertise in XFIG. Always, I said, I've got a paper's due tomorrow at 9 a.m. I need these 3 XFIG pieces.
Actually, our collaboration was extended to figures. So Emmanuel made all the figures essentially, so paid in chocolate from the Maison du Chocolat.
What's the status of the self-avoiding multi-local paper?
Well, at the moment, it's one of the least cited papers, but I recently noticed that Tom Hushcroft, who is visiting Orsay at the moment, a famous mathematician, recently looked at our papers thanks to ResearchGate. I learned from it.
Yeah, I think that's another thing that was mentioned earlier, and Manuel is a real physicist with on the mathematical side, which is, at least in my case, that the dimer vacancy problem has only a few citations, but I consider it one of my favorite papers, one very beautiful, I think, paper for me. And I think it's nicer than lots of my papers with several hundred citations. So don't follow fashion necessarily. Another inspiration from Emmanuel.